Hi, this is Mrs. LaBarbera. This is Physics Chapter 13, Modern Physics Video 3. Today's topic is Models of an Atom, Part 1. Objectives are: know different models of atoms, understand energy level diagram, be able to determine the energy needed to liberate an electron from an atom, be able to determine the photon energy needed or released when electron jumps to a higher or a lower energy level, and be able to determine if it is possible for a particular photon to be emitted or absorbed by a specific energy transition. First, let's see the history of atomic.
How do you picture an atom in your mind? Like this, or like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before. We've been talking a lot about the fine details of chemistry in recent weeks, and we're gonna keep doing that as we move on to nuclear chemistry, and then to the basics of organic chemistry. But before we do, I wanted to set aside some time to explain how we know what we know about the atom today, and how we know that we're not quite done figuring it out. Now you might think that once Leucippus and Democritus came up with the general idea of atoms, it'd be pretty easy for someone else to take that little indivisible ball and run with it. But you'd be wrong. The next major developments in atomic theory didn't come along for nearly 2,300 years. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds, by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. It's basically what a neon light is. Because this light was originally produced by a negative electrode, or a cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And very English Thomson visualized this model as a familiar English dessert, plum pudding, the positive matrix being the cake and the electrons the random floating bits bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium, they were positively charged, and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area, an area that he called the nucleus. Because most of the alpha particles passed right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles. Protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know! All the people I've mentioned and many others put their heads together over time to build this current and, I might say, quite elegant understanding of atomic theory. Now, after 2,500 years, even though we can't see them, we can know what they're like and how they work because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right. Scientists in Bohr's day fully believed that the planetary model was right, and today we're extremely confident that the quantum model is correct. But it may not be all the way correct, and that's where you come in. The only way we can go on being sure is to keep asking questions and conducting experiments.
So basically, this is a summary of the video, the history of atomic model. So you can take a look, pause it, and take some notes. Do a couple of examples. The diagram represents alpha particle A approaching a gold nucleus. By the way, alpha particle has two neutrons and 2 protons. So d is the distance between the path of the alpha particle and the path of a head-on collision. If d is decreased, what's going to happen to the angle? Look, this is a positive alpha particle and a positive nucleus. They will repel each other. So as d is decreased, that force will be bigger. Therefore, theta has to be bigger. Theta is increased. Another example, compared to a proton, alpha particle has. So what is the alpha particle? Alpha particle has 2 protons and 2 neutrons. So it must have 4 times the mass because neutrons has about the same mass as proton. So it's 4 times the mass and twice the charge. Another example, which diagram shows a possible path of alpha particle as it passes very near the nucleus. So we know that alpha particle and nucleus repel each other. So the only possible choice has to be 1 because all the others are attractive scenario, which is not what happens. Next one is Bohr model. So the Danish physicist Niels Bohr attempted to explain his model. The problems with Rutherford model is he was afraid it's going to collapse because the electrons is accelerating around the nucleus, and that acceleration will mean the energy decreases. Then it will result atoms to be collapsed. So, but that's not what happened. But Niels Bohr tried to explain it. So basically, he says no, they are not losing energy. That's how it is. And he also said electrons can only occupy certain energy levels. So all forms of energy are quantized. The electrons can occupy only certain specific orbits and not other. Electrons can jump from one to the other and emitting or absorbing quantums of energy in the forms of a photon. So can absorb light or release light. And each allowed orbit in the atom corresponding to a specific energy level. So the lowest energy level is the one closest to the nucleus. Here is his energy level. Ionization energy level, there is a ground energy level. Ionization means the electrons is escaped of the whole atom. So for an electron in the ground state, for it to escape, it would need a positive 13.6 electron volts to become 0. For energy equals to 2, if electron is at n equals to 2 level, it would need positive 3.40 in order to escape. So the energy level of an electron that has been completely removed from the atom is defined as 0 electron volts. All other levels are negative. Electron in the ground state has the lowest energy with the largest negative value. So ground state means lowest possible energy. So let's talk about more energy levels. So when electron is in a particular orbit, it is said to be in a stationary state. So each stationary state is an energy level. The ground state is the lowest energy level. Excited state is any states above ground state. And there is an ionization potential. That means energy needed to escape the atom, become ionized, energy becomes 0. So a photon's energy must match the energy level to be absorbed. Suppose that the electron is at n equals to 1 inside an atom. In order to go to 2, a photon must hit it with the energy level between 1 and 2. Similarly, from 2 to 3, only if the photon matches the exact energy that can be absorbed. That energy can be absorbed. Okay, so electron may jump to a higher energy level if it hits with a photon with just the right amount. So for example, from n equals to 1 is negative 13.6, and what is energy at n equals to 2? The energy of the photon has to match exact between 1 to 2. If it's a little bit more, it's too much, it's get rejected. If it's a little bit less, it's get rejected. Only if it exactly matches, then it is absorbed. Okay, so it has to match. An electron in the excited state will naturally decay to a lower energy level, will release a photon with the energy equals to the difference in energy between the level. So this causes the atom to emit photons with a very specific energy and corresponding to specific frequency. Here's energy level jump. So E photon equals to initial minus final, and the frequency we can use E photon equals H times F. You have to be careful from the energy diagram. This is in electron volts. In order to find the frequency, we have to convert electron volts to joules. So electron will jump to higher level again if absorbed photon has exactly the right energy. So when electron drops to a lower level, a photon is emitted. Let's take a look at an example. Explain why the hydrogen atom in N equals to 2 can absorb 1.89 electron volts of photon, but not 2 electron volts photon. Let's see, energy equals to 2. If you absorb 1.89, negative 3.4 plus 1.89, it will give you to negative 1.51. So that 1.89 electron volts photon will enable the electron to jump from N equals to 2 to N equals to 3. However, if you have a photon has 2 electron volts, and that is too much from 2 to 3, but not enough from 2 to 4. That's why 2 electron volts will be rejected. That's it for today. Thanks for watching.